What I'm going to do today is simply go over the ideas from each section. All right, so let's start with 5.1. 5.1, the topic is work and energy. And I'm going to go through the formulas for each section, and we'll talk about theory as we go through them as always. So the formula from the first section from 5.1 was work equals force times distance times cosine theta. Okay, this was the first formula that we started with. And this formula told us that if you apply a force for a given distance, you're doing work. You're accomplishing some work, assuming that the angle there is not perpendicular. And what I mean by that is this, and this is kind of an interesting fact. You can check mathematically with your calculator, but if theta were 90 degrees, the cosine of 90 degrees is 0. So you would not be doing any work when theta is 90. And here's what that means physically. It means that you're pushing on an object this way, yet it's moving vertically. So you're like pushing horizontally, but the object moves vertically. You're not causing it to move vertically, so therefore you're not doing work on the object. Again, that's the only circumstance where work will not occur, when the angle is 90 degrees or when the work and the displacement or distance or motion are perpendicular to each other. So again, say you have an object and yeah, you're not doing any work, although you might be exerting a force. One sec. So say you're applying a force of 200 newtons this way, but it's not budging. The object just isn't moving. And then there's another, I don't know, say there's a lever or a hydraulic lift below it, and the hydraulic lift pushes this up, and the object starts to move upward, so it ends up here as the hydraulic lift moves up as well. Oops, let me move that a little higher. So the hydraulic lift moves up, okay, it like pushes this object up, but you're pulling to the right. You're not doing any work because the direction of motion will be vertical and the direction of the force is horizontal, so this here is a 90-degree angle. Okay? When this is a right angle here, you're not doing any work. That's the only time that if you apply a force and something moves, you're not doing work, if the angle is 90 degrees. Okay, John?
If you, unless specified, that, like if you say you're moving an object straight, like no angles, you don't use cosine.
Exactly, unless it's specified that it's being pulled at an angle. So remember the example we did in the last chapter where you pull on a sled and you pull your like younger sibling along in the snow? The angle that you're pulling is at an angle, but they're moving horizontally. There you would use whatever it is, 30 degrees. Or maybe, you know, an object is moving up a mine shaft.
But what about the thing where it's,
like this, and there's a pulley right here, and there's a cord, and you're pulling at this angle here. So here's a pulley system right here. Okay, the angle is 30 degrees, and you're pulling with a force of Fp, yet it's moving vertically. Well, in that case, you would have to use cosine of 30. The angle, remember, theta is the angle between the force applied and the direction of motion.
Okay, so what about, how would you phrase it where it's going backwards so that cosine, it would be cosine 180?
Friction. Whenever it's friction, it's always cosine 180.
Word example?
Determine the amount of work friction does to the object as it's moved. Well, friction goes this way, motion is this way.
That doesn't mean that the object is moving backwards. It means
no.
That's just finding them. Okay.
It means that the force from friction is backwards, but the object is moving forwards. Peter?
Doesn't this just mean that you're not pushing right up to move right? Or why is it not moving?
I don't know. I mean, yeah, sure. You're not moving.
How is the angle 90 degrees moving right?
If the angle were 90 degrees, it's the only circumstance. So just given an example scenario, an object that's moving up, it's moving up on like some sort of a lift or a conveyor, and you're trying to push it off of it, and it's not moving. Well, it's moving vertically a certain distance, but not due to your force. Right. So you're not doing work. That's how you can theoretically understand it. Jack, then Marcus.
Isn't it if the degree is 180, it's also 0?
If a degree is 180, it's negative 1.
And 0 is 1.
Cosine of 0 is 1. Cosine of 180 is negative 1. That's why the work done by friction is negative. Because you're losing energy of the system, really. Marco?
So if there's no work, it's not moving, right?
It could be moving, but not due to the force that you're applying. It could just be moving on its own, and you try to stop it, and it just pushes you out of the way, and you can't stop an object that's moving into you. Okay? So again, you have to actually cause the object to move in the direction that you're pushing that's not perpendicular.
Sorry, I didn't hear you. It was cosine 0 is 1, and what is it, cosine?
180 is negative 1. Again, just to reiterate the friction part, if an object is moving to the right, yet there's friction pulling back or acting against its motion, technically speaking, what we want to do is think about this displacement down here so we can see that the angle is 180 degrees. Okay? So it's moving to the right, and there's friction pushing back against it. That's at an angle of 180. Cosine of 180 is negative 1. And that's why friction does negative work on an object. Again, friction does negative work on an object. Only time that doesn't happen is called rolling friction, a type of friction we haven't even started talking about. So don't worry about it for now. But there is one that is the exception to it. Okay? Rolling friction would be the exception. All right? So the idea behind work, before you just reiterate, force is being applied at a specific angle, and the object moves a certain distance. If you know those three characteristics, you can find the work done. Now, if I know the work done, and I know how long it takes to do that work, what else could I find from yesterday's lesson? The power generated. Again, power is the rate at which work is done. So if part A of the problem says, determine how much work is done, blah, 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 blah. Okay, you find the work done. Then part B says, if this operation is completed in 1 minute 30 seconds, how much power is generated, or how much power is the person delivering to the object? Well, the power that they deliver is the amount of work done over time. Okay, so you just take your answer from part A and divide it by the amount of time in seconds, so it would be 90 seconds, a minute and a half, and you could get the power generated by that person or mechanism or whatever it is. Okay? Are we all focused? Yes? Okay. Let's go to section 5.2. So this is how 5.1 and 5.4 are very much related. Okay, and then 5.2 and 5.3 are related as well. And then we'll see how that kicks into 5.4. 3 types of energy. One more. Kinetic energy. Potential energy, gravitational.
Oh, kinetic,
What was that word
potential
called?
spring.
Yeah, potential energy in a spring.
Oh, that's, yeah.
So it's like the same thing twice, yeah. So we have 3 types of energy. Now, kinetic energy is associated with an object that is doing what? Moving. It's got to be moving for it to have kinetic energy. Okay? We have gravitational, and then we have spring. Gravitational potential energy is associated with an object's height. Okay? Or vertical displacement, if you will. Some sort of change vertically, because it's due to the gravitational field, which acts vertically. Gravity does not pull us left to right, it only pulls us down. That's why potential energy, gravitational, is a function of height, some vertical change. And the spring's energy has to do with the spring's what?
Normal, constant.
Constant, but it's what? Compression or stretch. A spring could have a spring constant, but it might not be stretched. So it's really a function of its compression or stretch. So if you take a spring and you squeeze it together, you're storing energy in that spring, which is why when you let go, if you moved your hand, it would shoot off. If you stretch on a spring, all right, so say you, a bungee, you go bungee jumping. You jump off the bridge, the bungee cord's attached to you. Doesn't the bungee stretch? And that doesn't like pull you back up?
Yeah.
You're storing energy when you stretch a spring as well.
So you said that it's a factor of what again?
The stretch or compression, either one. The X value, we call that in the formula. Peter.
Sometimes, sometimes the mass was given in newtons, and other times it was...
Well, that's not the mass then. That's the weight of the object. So if you divide by 9.81, you'll get the mass. Again, if you're given the mass, you're going to use the mass because M is in these problems, right? But if you're given the weight of an object, if I tell you that the desk is 50 newtons, you have to divide by 9.81 to get the mass. How do you remember that? You remember that from this formula right here. Fg equals mg. If you're given the weight of 50 newtons, that's this number right here. And if you want to find the mass, divide by that 9.81 to get the mass. So that's why I said to you just now, always divide by 9.81 when you're given the weight of an object. If the units say newtons, it's the weight. If the units say kilograms, it's the mass. Okay? Now, we have three formulas here. Kinetic energy, potential energy, and then potential energy in the spring. Kinetic energy, formula. What do we got?
K equals kx squared.
Not kx squared.
No. K is 1. Something like
1/2 mv squared.
1/2 mv squared. Victoria, next one? Or so you had a hand up, I thought, no?
Oh, no.
Okay. Anybody for the potential energies? Potential energies. Dirks? MGH or MGY, very good. And for the spring? Again, go ahead.
K 1/2 kx squared.
Good. Okay, 1/2 kx squared. The kinetic energy and potential energy in the spring have similar looking formula, right? 1/2 mv squared, 1/2 kx squared. Now remember, what is x? X is?
The amount that's been compressed.
Or stretched. X is not displacement in this problem. It's the amount that the spring's length has been altered, whether it be stretched or compressed. Okay, that's what X is in these problems.
And if there's two, you just do the bigger one, subtract by those.
Yeah, so if you're given the free length of the spring, free length means its natural length. Say the natural length of a spring is 7 centimeters. And then I'm telling you that it gets compressed to 2 centimeters. Well, you do 7 minus 2, you get 5. And it really doesn't matter which way you subtract it because you're going to square x anyway. All right, for now. When we get to Hooke's law, we'll indicate whether it's positive or negative, what that actually means. Yes?
What is K?
What is K? K is the spring.
Kinetic. Oh.
No, force Fn.
It's a material property of the spring. We call it the spring constant or the spring stiffness, either word. Spring stiffness or spring constant. A higher K value means it takes more to stretch or compress that spring. So a spring in your pen would be a very low K value. A spring that's on your car, on your suspension system, would have a higher K value. If you put a spring that's on your pen in place of the spring on your car, your shocks would not work. It wouldn't actually make sense. And if any bump you hit, the whole car would start to do this. You need a stronger spring that could absorb the shock a little bit better. So as K goes up, the spring constant, okay, or the spring rigidity or the spring stiffness goes up. It becomes a more rigid spring itself. If you have a higher K value and you compress it pretty far, it means you're storing more energy. Okay, even more energy. And think about it logically. If you tried to take the spring that's in your pen, take it out and use it to launch an object, and you put an object on it and then let go, is it going to go very far?
No.
Not really. But if you get a spring that's maybe this long and the spring has a higher K value, it's stronger, and it takes a lot of force to compress it, and then you let it go, it'll launch pretty far. Okay? When we get to catapults, we're going to see how we can use what are called torsional springs. That's like if you took an object and started to, ever do like an Indian burn on someone's arm?
Yeah.
Where you take their skin and go like that to them? Now do that to an object. If you do that to an object that can rotate and then let it go, it'll unwind itself. And that's called torsional springs. There are such things as torsional springs. They're usually drawn like this. Here's how a torsional spring is drawn. And you take them like a clamp. Oh, we know this. Anybody when they were a kid ever see those things? They're called like they're working out your forearm. They're like hand clamps. And you sit there and you go like this over and over. And it's supposed to make you have strong forearms. It's really good for like baseball. Baseball players probably know of it. Okay, that's a torsional spring. It's a spring like this that you would sit there and squeeze together. And when you let go, what happens? The spring opens back up. That's a torsional spring. It's a little different than a spring that's a linear spring. Okay?
So that's bigger than actually.
That is different. The formula for this spring, side note, you don't have to write this down, but the formula for this is 1/2 K theta squared. because it has to do with how much you compress it, the angle at which it changes. But you don't need this for the test, okay? But it's just like a fun fact of something else for springs. There was one other thing in section 5.2 that we talked about. What was the last thing? It was a theory. That's 5.3. The blank blank theorem. Goober? Yeah, the work kinetic energy theorem. So let's talk about that for a sec. Yes, which again, you don't need the derivation. Here's the work kinetic energy theorem. The work kinetic energy theorem tells me the following. And you can write this in words, but it's already in your notes somewhere. The amount of work done on an object equals, I'm reading the formula. The amount of work done on an object equals the change in its
Kinetic energy.
very good. Kinetic energy. Alright, so if you apply more work or you apply a larger force and do more work, you're going to change the kinetic energy more, meaning you're going to make it go faster. And this was the example you took a video of where you slid on the ground with the socks. Alright? The work done in that problem was done by friction. It was to get you to stop. So your change in kinetic energy was a decrease in kinetic energy. We can also have a problem where it's an increase. Ready? I apply a certain amount of force to this. I'm increasing its kinetic energy. I'm causing it to move faster. All right? And as it moves along the ground, let's say I give it a start, right? The reason it stops, listen guys, the reason it stops is because friction does work, causing a decrease in kinetic energy. So a problem where I throw it, and it gets it to speed up, and then it slows down, it's actually two problems in itself. The first problem is work done by me pushing it, causing it to increase kinetic energy. The second half of the problem, when you segment it, is friction doing work causing it to slow down. So technically speaking, you could have two problems in one, where a certain amount of force is applied for a certain amount of distance. You could find the change in kinetic energy to get it to speed up. Then that force is removed, and now friction acts against it. That would be like the second half of the problem. Okay, so we talked about truncating or segmenting problems. That's the idea there. You need to look at a specific instant in time and say, here's the beginning. Well, here's the end of the first problem. Well, the end of the first problem is the beginning of the second problem now. And the end of the second problem now is when friction causes it to stop.
There is a problem on the problem set where it's like find the work done on a plane that's designed for vertical takeoff. And then so you find like the work of the point FP, I guess.
Okay.
And then, but how would you like find that or the other?
I need to read the problem. That's a little less context. I'm trying to think back to what it was. Anybody have the actual written? If she reads it, I can help. Give me a second. What, do you remember what? It was in section 5.1? Or 5.2? Oh, was it work kinetic energy theorem or just work?
No, sorry.
No, that was
I'll bring it to you, I guess.
Okay. Come ask me that. I don't know the problem off the top of my head. So, for a problem like this, you could expect on your test to be able to maybe determine the velocity of an object after a certain amount of work is done. So maybe you're told that a force is applied for a distance of 25 meters. Well, you have F, D, cosine theta over here, and you have final minus initial. Okay, that's what the formula always becomes as a result, really. And because you have work and you have kinetic energy, I don't give you this formula in the bottom. I give you the work kinetic energy formula, which literally says W equals delta KE. But you know W is FD cosine theta. Delta KE is change in kinetic energy, so you should be able to write this every time. Now, if a force is applied over a given distance, you've got the left-hand side of the equation. If the object started at rest, well, VI is now 0, you can find VF. Or maybe the object is moving initially, and friction does the work. So now that's going to be a negative number, but now this becomes 0 because final velocity is 0 because it's coming to rest. So the context of the problem allows you to use this equation appropriately.
In a problem like this with the degree that you give it to, or do you assume it's like 1 or?
Well, it depends on the context. It'll either be given, or it'll be a problem where it says like, the force is applied in the same direction of motion. Well, then theta is 0.
Yeah.
Or you could say friction does work, then theta is
180?
180. So if it specifies that it's 30 degrees, then yeah, you use 30 degrees. So maybe part A asks you to find the work done on the object. Part B says find the change in its velocity. And then maybe part C says find the power generated. Once you have the work done, you can find the change in velocity using this. Once you have the work done, you can find the power by dividing by the time it takes. So you can definitely expect a problem at the end of the test that has parts A, B, and C to them like that. Where you find the work in the beginning, then you find the change in velocity, then you find the power generated, and how they're all linked together to one another. Is that clear? I'm trying to give you little hints as to what to expect. So maybe make up a problem like this for yourself when you're home. Okay, think about a force that's applied over a certain distance. Pick an angle. As a result, find the work. Then if you know the work, give yourself the mass and find the final velocity if it starts at 0. And then maybe give a time period for yourself and find the power generated. You can make up these problems on your own, or at least look in your book, look for examples that are similar, okay, that have multiple parts to them. No.
How would you find the change in velocity?
So if you know the initial velocity, say it starts at rest or something, you could drop this off. Okay, and then if you're given all this other information, you could find VF. A lot of these problems have to do with finding velocity, or sometimes finding the distance an object travels. Like you apply the brakes on a car, and the brakes give a resistive force of some quantity, and the velocity you're traveling at is 60 miles an hour, and you want to find the distance it takes you to come to rest. A lot of those are like the skid mark problems, where like, remember you're with your socks, it's the exact same problem. Find the distance you slide in your socks, find the distance when you look at the tire marks that are on the road. That's how they determine how fast the person was traveling.
Starting with the forces.
Yeah, so if you know the force that the brakes can apply, which is really the force of friction, and you know the distance of the tire marks on the ground, forensic scientists can determine the velocity which you were traveling to see if you were actually the one at fault or not. So the tire marks left behind when you skid are really a function of the velocity you were traveling at. It also is a function of the weather conditions, right? If it's raining, the tire marks change and stuff. So all those things are considered. And the mu value is considered. So if you ever studied forensic science, you're going to see how there's chem, there's bio, there's physics. It's all in that topic. So somebody that was specifically looking at that, or a forensic analyst that was looking at that problem, needs to definitely know their physics to do that. Okay? So you could expect a problem like that on your test, where it's an application, where a car travels and it skids or something like that. Or force is applied and it slows down or it speeds up. Okay? Definitely expect that as a math problem.
Like a long answer, or like I'm asking,
Oh, the end ones.
like the last.
Yeah, like parts A, B, and C style, like I was saying.
You would give the mu value if it were to be for friction.
If you had friction, you would be given the mu, and you'd have to do mu times Fn. Realizing that Fn is mg in these problems because there's no vertical forces acting on it. Or maybe I'll give you the force of friction that you actually feel. I'll say friction exerts a force of 70 newtons. Well, then that's 70. This is cosine 180, and maybe you have to find d if you're given this other information. Okay? But you got to see how these are all related to one another. Section 5.3. Section 5.3. What was Section 5.3 about? What was Section 5.3 about? You did the homework for it today. Dirks? Yeah, conversion or conservation of energy. The one and only formula you have in this section. All right, that's it.
What does that mean?
What does that mean? Dirks, what does it mean? Final kinetic, yeah.
You read it.
Okay, so all it means is this. Take the energy before, set it equal to the energy after. It depends on the problem. There's no one right or wrong answer here. It depends on the context. For example, let's do an example. All right? An object starts at a height of 8 meters above the ground in a spring-loaded setup scenario. Okay, so I draw a picture. Here's a spring and there's an object on the end of the spring. The spring is compressed a given distance. I don't care what it is for now. And it's at a certain height. And the question asks us, determine the velocity of the object or the impact velocity of the object. Impact velocity. So what's going on in this problem? What kinds of energy do I have? Jack.
Potential, like initial potential?
Okay. Because of the height,
Yeah.
right?
And when it's launched, like don't you have kinetic energy? Is it being launched off this thing?
It is eventually being launched, but again, it's loaded in a spring.
So K, no, we have, and do we have, no, K, we have K?
You don't have K. It's not moving. It's loaded in a spring.
Okay. Is that all you have?
Potential of the spring.
Potential of the spring also. You have the gravitational initial, and you have the spring energy as well. Remember, a spring is not going to be in the beginning and the end of a problem, so I don't have to give it a subscript. You follow what I'm saying there? I don't have to put PES and then put an I there because it's either at the beginning or the end. It's rare, and you're not going to get an example of that. But you can think of an example where there is a spring at the end, but not the beginning. I can think of one off the top of my head. What's a scenario where there might be a spring at the end of the problem? If this person landed on what? A mattress, a trampoline, something like that, right? Well, then it would have energy at the end, and you have to do some work there. Or maybe the Metro North or along on the railroad cars. At the end of the track, there's a spring there. Ever notice that? In case the brakes fail, and the train, instead of running into the station, would hit that spring, which would absorb the energy and would act as like a shock absorber. Okay? Peter, what's at the end of the problem? What kind? Question?
Like, it's only for the PE of any. You only use the PEI and PES, right? You don't use the PES, right?
Well, in this problem, there is spring in the beginning energy, and there is gravitational energy in the beginning. So those both go in the beginning. What happens, though, over here, guys? What kind of energy does the person have the instant before he hits the ground? Thank you. KEF. Very good. Okay? So, here's what I do. This is the beginning of the problem right here. So I put those on the left-hand side of the equation. And then at the end of the problem is only KE, so we put that at the end of the problem. So every single problem is different, but it's the same governing law, MEI equals MEF. Conservation of mechanical energy. Okay, conservation of mechanical energy. I specify and say mechanical because you could have internal energy, you could have bonds that are broken in a molecule which release more energy. We're looking at mechanical energy here.
It is called.
Okay?
Wait, so that's it? That's just
Doesn't matter, it just depends on the problem itself.
PES.
Now, let's say, what are you looking for in this problem? What did I ask you to find? The impact velocity. So you have to then plug in your formulas for these three and try to isolate V.
Is impact velocity just VF?
Why?
Correct.
Why? Why can't you just KEF?
Sure, you could find KEF, but the problem says find the impact velocity, which is embedded in KEF.
So there are multiple options of what MEI is and equals MES.
Exactly. MEI and MEF can be comprised of many things, but once you write down this line, then it's easy. You just plug in the formulas, you know. You know these formulas, they're given. Spring energy is 1/2 kx squared, given. mgy is potential energy, given. Ke is 1/2 mv squared, given. So you don't really need to do much more. Now you just have to use algebra. It's an easy problem at this point. If you know how much the spring is compressed, I see your hand, Peter. Give me a sec. You know the rigidity of the spring. You know the mass of the object. You know gravity. You know the height it was starting at. And again, I said you know the mass already. You can find VF. So it depends on the problem. Maybe I'll give you a problem where it says the impact velocity is 27 meters. What height should it be launched from? Then you're solving for y. You follow what I'm saying now? The problem can be manipulated in easy ways. It can be changed very simply. Peter.
So for MEI or MEF, if there's PES and PI, you do both. And then
Sure.
So it would,
Whatever energies you've got.
if KEI wasn't 0 here, you would have done PS plus PEI plus KEI.
Absolutely. Absolutely. But I'll tell you this much. When an object is loaded in a spring, it's never going to have kinetic energy because it's not moving. It's at rest.
Okay.
And then it's launched. So whenever you have 1/2 kx squared, you're not going to have KE on that side. All right? It's the same example of this. A train is moving with a certain amount of kinetic energy. Well, that goes in the beginning. And then to stop, it has to hit the spring. Well, the spring is at the end now. So these would be switched on both sides. But they're never going to appear on the same side. Okay? Go ahead.
What exactly is mechanical energy? Because I'm confused as to how the kinetic correlates with the potential.
So mechanical energy has to do with the energy of an object's motion or position, really.
Okay.
So it can be compressed, position change. It can be at elevated height, position change. Or it can be moving, kinetic change. So it's just kinetic and potential energies. That's what mechanical energy is.
All right.
Because you can have internal energy where, like, for example, like something like a grenade, where there's some chemicals inside of it. So that's now chemical internal energy, very different than mechanical. Okay? So we're going to just look at those specific things. So for those that may have struggled with the homework, this might help you. This concept, this idea. Okay, and that's what I went over in class in the first 2 examples, and that's what those last 3 examples that you were to watch over the weekend were trying to illustrate. That the problem may change, but the governing equation is always this. Okay, that's always the governing equation. Now, there's one alteration to the equation I mentioned in class. What is it, Marco? Yeah, what is Q loss? What's the deal with that Q loss? What do you got? Go ahead, Marco.
When there's friction.
Yeah, these problems are assuming there's no friction. If there's friction involved, then you get this Q loss at the end of the equation over here. Alright? It has to do with the energy lost due to friction, or the work done by friction. So most of the time, Q loss becomes something like this. F d cosine theta. Okay, Q loss is usually Fd cosine theta, and it's energy that's lost to the force of friction acting on the object. So let's say this problem now involves air resistance, and I tell you that the air pushes back with a constant force of 30 newtons over a distance of 20 meters. Well, so 30 times 20 gives you 600, so 600 joules of energy get tacked on to the end of this problem maybe, depending on the scenario. But it always depends upon the context of the problem.
Which
Yeah.
is that what Q loss is?
Q loss is usually energy lost due to friction. And the formula you're going to use, if it's energy due to friction, is the work formula. Okay? So Q loss is really the work done by friction. You see how these things are all related? Section 5.2 is related to 5.3. This is kind of like the work kinetic energy theorem. The work kinetic energy theorem is really just another way of using mechanical energy balance. That's all the work kinetic energy theorem really is. All right? Any questions? Any questions on 5.3? We'll do an example at the end. Trying to get through the theory, because the theory is what helps you in these examples.
We have 2 minutes.
We have 2 minutes, that's
Yeah,
it?
it ends at 30. It's 30 seconds.
All right, we have 2 minutes. Let's do quickly section 5.4. Okay, section 5.